Hi, fantastic fourth graders. Miss Fallon here. I'm going to be reading your science lesson, one of them for this week, and then I will be reading the second one a little bit later. Right now, I want you to get out your booklet for science that has the title, it says Forms of Energy. That's what we're going to be working on for this video. You can have a pen or a pencil also so that you can jot down notes if you would like. I want you to take a look at the page that says before reading. It wants you to make an idea map. Now, you can just use this page for your idea map if you would like, so you don't have to create one from scratch. In the center, it has energy. What we're asking you to do is each blank oval to write in what you know about different forms of energy. We're not asking you to do this before the activity, just create the idea map. And then as I'm reading, you'll be learning about the different forms of energy. And you'll be able to, at the end of the lesson, jot down what you learned and what you now know about different forms of energy. I'd like to go ahead and activate our prior knowledge on energy, what we've learned in the past. On that same page, up here in this blank space, I'm going to give you about 1 minute, 60 seconds to go ahead and jot down one or two things, what you already know about energy. Anything that you know. There are no wrong answers. Just what do you already know about energy before we get started on the lesson? I'll give you about 1 minute to go ahead and do that, and then we're going to go ahead and start reading. Okay, go ahead and stop where you're at. No big deal if you didn't finish. This is just to get our brain flowing, activate our science investigative skills, and figuring out what energy is. I want you to go ahead and look at the booklet that we've provided for you. There are a couple of different text features that I want to point out as we're going through this booklet. The first being the headers. There is a header for each section. And the header is the text feature that tells us what we're going to be reading about in that section. Another text feature I want to point out is the bold words. There are bold words throughout the booklet. These are words that are vocabulary words for science that we need to know. If we're not 100% sure where in the paragraph to find out what that word means, there is also a glossary at the back. And in the glossary, every bold word throughout the booklet is listed with the definition of what that word means. This is a great resource for us if we're not 100% sure on the meaning of the word. Another text feature I want to talk about are at the bottom, they have pictures. Some of these pictures, it's a little hard to tell what's going on in the pictures, but in the top corners of some of these pictures, bottom corners of some of these pictures, there are what is called captions. And captions explain what's going on in the picture. Even if we can't completely see it because it's a little blurry or it didn't come out right, we can still go ahead and take a look at the captions. Now, some of the captions are very light, so it'll be hard for us to read. I'm going to try and explain them as best I can if I can't read the captions. Okay? So we're going to go ahead and we're going to get started. I want you to read along with me so that we can build our reading skills as well as science today. I'm going to use my finger and I'm going to follow along. Now, as always with reading, we read everything on the page. So we're going to start with the header up at the top, and I'm going to put my finger on the first word of the header at the top. We're going to go ahead and start, and I want you to follow along. I think this is a great activity while you're at home to go ahead and read out loud with me. Forms of energy. Turn on a light, rub your hands, you are using energy. Energy is the ability to cause motion or create change. There are many forms of energy. The next header tells us one of the forms of energy. It says electrical energy. Electrical energy is the movement of electric charges. Electricity runs toasters. Electricity runs computers. Pretty much anything you could plug into an outlet in your home, at school, to get electricity. The next type of energy for the next header says thermal energy. Thermal energy is the energy of moving particles in matter. You can feel the flow of thermal energy as heat. It is used to cook food. It is used to warm homes. Notice at the bottom there is a picture of an electrical substation where we get our electricity through the wires. It does not have a caption. It's just a guide to show you this is what it looks like when electricity is being sent out to different homes and apartments in cities. Looking at the next page up at the top, the header, sound energy. Sound energy is caused by vibrations. Sound travels through air and water. Sound travels through other matter too. It cannot travel through empty space. You use sound energy when you listen to music or talk to a friend. Next header, light energy. Light energy moves as waves. Light energy can move through empty space, whereas sound cannot. Light energy from the sun moves through space to Earth. Plants use light energy from the sun to make food. And you'll notice in the picture of the sunflower, there's a caption in the top corner. The caption's going to tell us what it's showing us in the picture. And the caption, it says, light energy helps plants grow and make their own food. We're going to go ahead and flip that over, and now we're looking at the header that says potential and kinetic energy. Okay, you're following along just like me. Here we go. Potential and kinetic energy. Potential energy is energy that is stored in an object. Potential energy can change into another form of energy. A toy car at the top of a ramp has potential energy. It's not moving, it's just sitting there. When the car rolls down the ramp, potential energy changes to energy of motion. Well, what's energy of motion? Let's take a look at the next paragraph. Kinetic energy is the energy of motion. Anything that moves has kinetic energy. Kinetic energy can be changed to potential energy. When the object stops moving, it then goes back to potential energy. Looking at the picture at the bottom, it's very hard to see, very light. It has A down here by a student's hand, B kind of halfway up, C up above the student's head, and D on the other side of the student. I'm going to go ahead and read them step by step. This is a student that is juggling an orange. So A, down by the student's hand, it says the orange gets kinetic energy when it is tossed into the air. In the hand, tossed in the air, it is moving, which is kinetic energy. Looking at B, it's a little further up, but not all the way to the top. It says, as the orange goes up, its kinetic energy changes into potential energy. So, it's now going to be changing from kinetic energy, or energy of motion, into potential energy, energy that's stored in an object. Looking at C, C is up above the student's head. The orange has the most potential energy when it's at its highest point. When it comes all the way up to the top, as high as it can go, it kind of pauses there, even just for a half a second, and that creates potential energy again because it's kind of held there in the air at the highest point possible. Looking at D, you'll see it's coming back down. Well, when it comes back down, it's moving again, which is called what? That's right, kinetic energy. So looking at D, the caption says, as the orange falls, the potential energy changes back into kinetic energy. Looking over at the next page, we're going to start with the header at the top, forms of potential energy. There are different forms of potential energy. One form is gravitational potential energy. Now, as we've talked previously when we covered our science and space unit, gravity is what holds us down on Earth. Astronauts float in space because there is no gravity. So gravity pulls us down and holds us down in place so that we're not floating around. The toy car at the top of the ramp has this form of potential energy. The energy is stored until the car moves down the ramp. The gravitational potential energy of the car is here at the top. It's called gravitational potential energy because gravity then moves the car down by pushing it back down to the ground. Next paragraph. A stretched rubber band has elastic potential energy. Let go of the rubber band and snap, the energy will change to kinetic energy because the rubber band has moved. Food has chemical potential energy. When food is eaten, this energy can change into other forms, like the energy that we use to play sports or games or run around outside. Looking at the picture at the bottom of this page, it shows two kids in swings. Notice they're high up in the air. And look at the caption. A swing at the top of its motion, so all the way up at the top there, as high as it can swing, is gravitational potential energy because it kind of pauses up at that high point and then the gravity pushes the swing back down. Let's go ahead and turn to the next page. We're looking at the header, how sound travels. Sound is energy in the form of vibrations that pass through matter. When an object vibrates, it moves back and forth. Sound energy moves through solids and liquids. Sound moves through gases too. So all states of matter, solids, liquids, and gases. Very interesting. It cannot move through empty space. You hear sound because your eardrums, located inside your ears, vibrates. Think about a guitar string that vibrates. The vibrations pass energy to the air. The energy moves as sound waves. The sound waves move through the air. When they reach your ears, your eardrum vibrates. You hear the sound made by the guitar string. The picture shows a little girl playing a guitar, and the caption says, plucking the guitar string makes it vibrate. This causes sound waves to move through the air. Looking at the next page, header at the top says sound waves. When sound waves move through air, they move the particles that make up air. The particles form a pattern. In some places, particles are close together. In other places, particles are further apart. The part of a wave where particles are close together is called a compression. You can see a compression when the coils of a spring toy are squeezed and squished together, and then the compression is released and the toy bounces. Looking at the picture of the drum, it shows us the sound waves These are labeled as compression because they're tightly close together. Looking at the caption, it says, sound waves move through air when the drum is hit. The particles of the air show a pattern of compressions. Flip it over, and we are now looking at the page that says frequency and wavelengths. Starting with the title, following along. Frequency and wavelength. Sound waves have properties. The frequency of a wave is the number of waves that pass a point in a certain amount of time. Frequency is often given as the number of cycles a wave makes in a second. One vibration is equal to one cycle. Wavelength is the distance between the high point on one wave and the high point on the next wave. Looking at the picture, it shows us a computer model of electronic signals. And it shows us a wave pattern. And it has labels for a diagram breaking down the different parts. So the measurement from the highest point of this wave and the highest point of this wave is wavelength. Looking at the next page, we are reading the header, pitch and amplitude. The frequency of a sound wave affects the sound's pitch. Pitch is how high or low a sound is. Some sounds have a high frequency and high pitch. These sounds come from objects that vibrate quickly. Other sounds have a low frequency and low pitch. These sounds come from objects that vibrate more slowly. Some sound waves are stronger than others. Strong sounds have more energy and are loud. A loud sound has a high amplitude. Amplitude is the height of a wave, measured from its midline. And if we're not 100% sure what the word midline means the center. The louder the sound, the higher its amplitude. And if you look at the picture here that it is provided for us, this is the A wavelength, this is the B wavelength. This line going across the center is the midline for each set of waves. The line going from the midline down to the bottom is the amplitude. Notice that A is shorter than B. The caption tells us that B has a higher amplitude because it's longer, so it is louder than A. Flipping, we are now looking at the page that says wind energy. Wind energy. Wind is air that is moving. Moving air has kinetic energy because at the beginning, remember, we said kinetic energy was the energy of motion, and the wind is always moving. Winds that are fast enough can move objects. Have you ever seen a sailboat move across water? Then you have seen wind energy at work. People have found many ways to use the kinetic energy of wind. Windmills were once used mainly to pump water or to grind grain. Today, or now in modern times, wind turbines are used to spin generators to make electricity. Wind energy causes the arms of the turbine to spin. And in the picture, it's hard to read the caption, so I'm not going to try. I'm just going to explain the picture to you. The picture shows wind turbines out in a big open field, and there's blades at the top of the wind turbines that as they turn, they're collecting the energy from the wind blowing through them to produce electricity. Looking at the next page, We are looking at the header at the top that says energy from moving water. Like moving air, moving water has energy. Water flows from high places to low places. The flowing water can be used to move parts of machines. Flowing water was once used to spin water wheels and run other machines. Today, some power plants use the energy of flowing water. Hydroelectric power is electricity that is made by using the power of moving water. And we could figure this out remembering our previous lessons on Greek and Latin root words, understanding and remembering that hydro means water. Looking at the picture, up at the top, it is titled Hydroelectric Power Plant. Then it has 3 labels, so it is a diagram of a hydroelectric power plant. It has 3 labels that are labeled 1 over here, 2, and then 3. I'm going to read each one. 1. Water moves through pipes in the dam. Notice it travels down to number 2. 2. Moving water turns the turbine. Then we're looking at 3. The turbine turns the generator, which makes electricity. Flipping it over, we are looking at heat and conduction. Heat and conduction. Hold a hot mug in your hands. Your hands will feel warmer. Heat is the transfer of thermal energy between matter of different temperatures. Thermal energy moves from the mug of hot chocolate in your hands. It always travels from warmer objects, or the mug of hot chocolate, to cooler objects, or my nice cool hands. Conduction is the transfer of heat that happens when one thing touches another. A bird sitting on her egg is an example of conduction. The bird's body is the heat source. Conduction transfers the thermal energy, or the heat energy, from the bird's warm body to the cooler eggs in the nest. And in the picture, it shows an eagle in its nest. We can infer that there's eggs under the eagle, but let's take a look at the caption. The eagle warms its eggs through conduction. So our inference was correct. There are eggs underneath the eagle, and the eagle is using its body heat to warm the eggs in the nest. Looking at the top of the next page. A conductor is a material that allows heat to move through it easily. Iron is a good conductor. Copper conducts heat well too. Cooking pots are made out of metals that are good conductors. These metals do a good job of transferring heat to the food in the pot. An insulator is a material that limits the amount of heat that passes through it. Wood is a good insulator. It does not get very hot. Some plastics are good insulators too. Looking at the pictures, there are 3 pictures. The first one is a picture of a frying pan. Looking at the caption next to it, it says, iron, so this is an iron frying pan. Iron is used to make pans because it is a good conductor of heat. The iron pan allows the heat from the stove to go through it to cook the food. The next picture, it's a little harder to see, but it is a long wooden spoon. And that caption reads, the spoon is made of wood because wood is a good insulator of heat. It allows us to use the wood spoon to stir the food that's being cooked without making the spoon so hot that it burns our hands. And the final picture at the bottom kind of just looks like a big square. It might even look like a pillow, but it's not, I promise. What it is a plastic food container. And the caption says, many foods are served in plastic containers. The plastic is a good heat insulator and keeps the food warm. We are on our last page. We have 2 more headers. We're going to go ahead and start up here with heat and convection. Using our fingers, we're still following along, hopefully. Heat and convection. Walk past a stove when the oven is on. You'll notice that the air near the oven is warm. Convection is the transfer of thermal energy as matter moves. In convection, a gas or a liquid moves from place to place. When the air in an oven heats up, air particles move quickly. Some move upward, out into the rest of the kitchen. Then cooler air from the kitchen moves into the oven. A pattern or current is formed. Warmer air moves upward, cooler air moves downward. And it's trying to show us the pattern or the current in this picture because warmer air moves upwards, cooler air moves downwards. Let's go ahead and take a look at this heading over here. We're going to read the last section. It's really hard to read these, but again, these are labels that are labeling the parts of the diagram. And this is a diagram showing the current or the pattern that the air flows. So looking at our header on the other side, it says heat and radiation. Heat can move in other ways too. Radiation is energy that is sent out in waves. The sun warms Earth with radiant energy. When this energy hits you, the particles in your skin move more quickly. The radiant energy is changed to thermal energy. You feel warm. Radiation can travel through different kinds of matter. It can also travel through empty space. Look at the diagram of the greenhouse on this page. The yellow lines, and I know there's no yellow because we copied in black and white, but the lines, the arrows, show that radiant energy from the sun, which is all the way up at the top above the greenhouse, warms the ground. So the sun heat travels down to the ground to warm the ground. Then the next arrow shows us the warm ground then warms the air up above it inside the greenhouse. On the back, again, you have your glossary, all your bold words with the definitions of the bold words. After reading. So I'm going to go ahead and read you quickly the 4 questions about after reading, and I'm going to just kind of show you a little bit which header you'll be able to find the information if you're not 100% sure. If you are, great. I think that's fantastic. But if not, if you still need a little bit of help finding the answers, that's what I'm here for. So go ahead and take a look at the page that says, after reading, did you understand? I'm going to start with question 1. What is the difference between kinetic energy and potential energy? 2 ways you can find this answer. Kinetic energy and potential energy are both bold words, so they are listed in your glossary. If you don't want to look in your glossary, you can always look on the header that says potential and kinetic energy to answer this question. Looking at number 2, which one has kinetic energy? Now, since we just talked about the difference between kinetic energy and potential energy, hopefully we're quickly able to identify which one has kinetic energy. Looking at the 2 pictures, the first picture is of a flag flying in the wind. The second picture is of a rock sitting in the grass. Look at number 3. Number 3 says, what is one way people use the energy of moving water? Now, great. If I'm thinking back to our lesson, I'm looking for the header that says energy from moving water. That would probably be the best section for me to answer this question. And finally, question number 4. One sound is soft and one is loud. Which sound wave has a higher amplitude? For this, we need to go back to find the page that says pitch and amplitude for our header. This is great information to help us answer this question, and the picture at the bottom clearly shows us what the wave would look like for the amplitude if it was loud or soft. Hopefully this helps you answer your questions. I'll be posting a little bit later the second science lesson video. I hope you guys have a great day and stay safe and healthy.